Okay, welcome to 1 o'clock on a Friday where you're sitting in fluids for one of the last Fridays that you will be sitting in fluids, which is always kind of an exciting thing. We're getting near the end, but we're not quite there yet. I know this is the time of year that all of us are scrambling and doing things all at the last minute, myself included. So no shame in that. But I wanted to spend a little bit of time at the start of today's class just going over some stuff about the project that you all have been working on. Been getting a number of different questions about some of the same things, so I want to just make sure we touch on that and give you a chance to ask questions before we dive into kind of new material. Number one, don't swim by the mouth of pumped hydro stations. They might suck you in. So don't do that. Don't be this guy. When you're thinking about how these things work, okay, I don't know. I think maybe some of the equations that we use can confuse us and keep us from thinking about things rationally. And they just turn into equations and we just use them and we forget what they mean. So if you're looking, right, we're looking at energy in fluid. We're using energy in the water to do something. The water starts with potential energy, and then we take some of that out and we use it and turn it into electricity. At any point along the system, right, where the energy that we can use is the mechanical energy of the water. We can't use the thermal energy of the water, so that's what we call losses. So at any point along the system, say like here, we can characterize the amount of energy in the system by like pressure over density plus alpha v squared over 2 plus gz. So whenever we're writing that, all that is saying that's how much energy we have at location 1, location 2, location 4, whatever it is. And then what we're doing is we're characterizing the changes in energy between one point and another point because something happened. So for example, if we start up here at 1, how much energy do we have at 1? Well, it's going to be V1 over rho plus alpha 1 V1 squared over 2 plus G Z1. Now some of those might be 0, but we can track all of the energy that we have at 1. Then we can watch that fluid as it moves from location 1 kind of down our channel, right? It's moving down this way. Say the next time we want to take a look at it is right there at 2. Well, how much energy do we now have at 2? All of the energy that we had at 1 minus anything that we lost from friction, right? So conservation of energy tells us that like unless we lose energy, unless the energy changes to some other form or we like put it in or take it out, energy is conserved. So the energy at 2 should be equal to the energy at 1. I'll write it this way. 2 should be equal to 1 minus our losses. So this would be minus what we call the head loss. And there are different ways that we can figure out how much head loss we have, how much friction we have, how much energy we're losing to friction. Then you can look, say, right there at 3. Say, okay, so the fluid at 2 has lots of energy still. Not as much as at 1, but it still has a lot. We only lost a little bit to friction, hopefully. How much do we have at 3? Well, we want to now like use the turbine and be extracting energy because that's like the whole point. So we're going to be removing energy from, as we move from 2 to 3, the energy that we have remaining at 3 is equal to the energy that we had at 2 minus the head loss of our turbine. We call it turbine head loss. That's how much energy we actually took out of the fluid. And you can keep going either up or down. thinking about it kind of in this framework. But I think if you think of like defining a point and saying how much energy do I have at that point, and then I'm moving to a new point, how much energy do I now have at my new point? You can do it either like, right, you can do it in kind of multiple steps like this. Like first I move from 1 to 2, then I go from 2 to 3, then I go from 3 to 4, and I'm finally done because I'm in Lake Michigan. Or you can go it in like one big jump all the way from 1 all the way to 4. So how much energy do I have at 4? Well, I started with this much at 1. Right, I started with this much at 1, and then I came down here and lost some to friction, lost some to friction, lost some to friction, lost a huge amount because I took it out to work. And then I lost some more to friction, lost some more to friction, lost some more to friction, and now I'm here and I have this much energy. You can do it in like a single step, or you can break it up and do multiple steps. For me, it makes more sense and I make less mistakes doing multiple steps. That's true just like general problem solving. I'm always trying to break up problems into small steps so that you don't screw up, because otherwise you're trying to keep track of too many different things. But I think, right, just kind of recognizing the fact that that equation, all it is talking about the mechanical energy that the fluid has at a certain position. It's tracking all the different forms that it might show up as. And then we're using head loss to look at how that's changing as we move to different places in the system. Okay. We have a few minutes yet for questions. If anybody has questions either on this or just more generally on the design problem and write-up or things like that. Are there any questions? Okay, any virtual people have questions, you can throw them in the chat. Okay, no questions. So one question that was asked in the last class was a little bit to do with, like, how do you know what to vary, and like how much time should you spend trying to vary stuff? And I guess I would say once you have a model that's up and working, one strategy that I think would work well is if both of you take that spreadsheet and each of you separately, each of your teammates separately spends 20 minutes changing variables and trying to get just like an intuitive feel for which ones matter and do they matter a lot, and like if I make this bigger or smaller, how does that change things? Because once you have like the framework laid out, all of those things should kind of solve all themselves. So if you change, for example, the friction coefficient, you'll see how that changes things. If you change the minor loss coefficient, like the K values, if you double it, does it matter? How much? If you cut it in half, how much does that matter? And then you can try to start just even in some, as short as 20 minutes, you'll get kind of a feel for what things are, make big changes to stuff and what things make little changes to stuff. And you can start to key in on what are the things that we really need to focus on to get our system optimized. Like what are the things of first priority versus the things of third priority. So for example, if minor loss coefficient, the K values, you look those up in tables. What if you multiplied it by like a factor of 2? What happens? Does essentially nothing change? Or do you see like we added more friction, we see a little bit of a change, or we see like, hey, that actually changed our final efficiency by like 10% or 5%. Like that's a big deal, 5%. We really have to key in and make sure we're designing our system with the lowest possible minor losses. So that would be something that could come out of your report that you're writing. Like if minor loss coefficients change the overall system efficiency significantly, you want to make sure you highlight that in the report so you can say, hey, this is how we optimized it, but when we design our final system, this is a part that we really have to key in on because this is hugely important to the performance of the system. So we're really going to have to look at, how are we designing inlets and exits and bends and make sure we use really low loss valves and all of these things. We're going to have to really focus in on that because it matters a ton. Now, if on the other hand, you change this and you change the minor loss coefficients by a factor of 10, and your efficiency for your whole system goes from 70 to 69.94. You go, wow, these don't matter. Nobody cares. We'll do it later. It has almost no bearing on the performance of the system, so we don't need to worry about it. Let's focus on the other things, the higher priority things. So those are the kind of questions that you want to be asking, like pipe diameter. If you go from a 5-meter pipe to a 6-meter pipe, do things change a lot, or do they change just a tiny bit? You want to focus in and make sure you're keying in on the parts of the system that matter the most. And again, just trying to, I think spending 20 minutes or something like that, each of you separately, just try to get a feel for what matters. And then you can come back together and talk about that. That's how you can decide, like, what are the things that we really want to focus in on in terms of optimizing our system. Because you want to start with the things that are like the biggest effects and get good values for that before you start to try to optimize other parts of the system. Okay. Yeah. Any other questions now that you've thought about things a little bit more, or I've talked about things more? Okay. We feel like we're in a good spot. So the reports are due end of the day on Monday. I will try to be at least moderately available this weekend. If you do have a question, shoot me an email. I'll take a look at it and respond as soon as I'm able to. But I know this is like the time of the semester where we're all working last minute, so I'll try to, I'm not going to totally, promise I'll be available in 5 minutes over the weekend, like maybe sometimes during the week, but I'll try to be available by email at least. Okay, so if there aren't any other questions now, we'll dive into some new stuff. Okay. All right, so where we ended last time, don't necessarily write all of this down, but we ended with a dimensionless version of the Navier-Stokes equation. So hopefully you see this in your notes from last time, just to remind yourself. We had the, I'll just write the y component so I don't have to write everything. The y component was u star dv star dx star plus v star dv star dy star equals minus gl over velocity squared minus d pressure star dy star plus mu over rho VL d squared v star dx star squared plus d squared v star dy star squared. Okay, it's a big ugly equation. We made it dimensionless. And why did we make it dimensionless? Well, we made it dimensionless. We'll see a little bit more, but right, all that the Navier-Stokes equation is, it's this big nasty thing, but it's just a force balance. So this part, that's acceleration, fluid acceleration. How is the fluid moving? Which is governed by the forces that are being applied to the fluid. And if we have one big force and two itty bitty forces, the big force wins, and that's what's governing flow. If we have two big forces, then we have to consider both of those. If we have, if gravity is a big force and other stuff is not, then we really only have to consider gravity and we don't have to care about the other stuff. So the advantage of putting it in this kind of form is it allows us to look at what are the big forces, what are the things that we actually have to worry about, and what are the little forces, what are the things that we can cross out and we don't have to worry about. So this is like a non-dimensional gravity. We call this the Froude number. This is a non-dimensional pressure. And this is, that's 1 over the Reynolds number, which is for viscous forces. Okay, so this whole term is, that's an ugly bracket. So that whole last term is from viscosity. Okay, so what forces are important? Well, we can use these different, like the magnitude of those different groups to tell if that is big or if it's small. So for example, the flow that we looked at where I had this cylinder and I turned the inside cylinder and it like mixed up the food coloring, and then we turned it back the other way and it unmixed it. That was a flow where Reynolds number was super small. So what governed the flow was not gravity or pressure or inertia. What governed the flow was viscosity. So it was a small Reynolds number. Viscosity was winning. When we looked at, so example, if Reynolds number is small, viscous forces govern the flow. So think of, I don't know what to call it. Think of like the laminar flow, reversible flow experiment that we did in class. Another system that we spent quite a bit of time looking at was what we call Euler's equations. So this was, remember, this was no viscosity. Viscosity equals 0. So if so no viscosity, frictionless flow. So what this means is the Reynolds number is equal to infinity. So 1 over the Reynolds number is equal to 0. So if we look at the Navier-Stokes equations, the viscous forces stop mattering. And what governs flow? Well, this was when we talked about like gravity and pressure. So pressure differences are governing flow. So we could use Euler's equations. This gave us Bernoulli's. And essentially we got, what does fluid acceleration depend on? How does fluid move? Well, it moves only in response to pressure gradients. It flows toward low pressure and away from high pressure, and it curves around areas of low pressure, and it curves away from areas of high pressure. And that's how we looked at forces on like an airplane wing. And we could do that because the Reynolds number was essentially infinity. it was really big. So we knew that the viscosity term didn't matter and we could just look at pressure. So looking at a kind of fundamental physics, when we try to boil it down into non-dimensional groups, it's a way without having to do any of the hard work of actually like doing significant calculations. You can figure out what are the key forces and what are the key factors that are influencing this system. So do pressure differences influence the system? Well, they do if your Reynolds number is really high compared to pressure, but they don't if the Reynolds number is really low. And like, you know, this term, 1 over the Reynolds number is big. So like if this, right, viscosity works if this guy wins, if that term's really big, if that's a big force compared to, say, some of these other ones. You should have in front of you, for those who are virtual, this is online, just a handout, a short handout on dimensionless groups. These dimensionless groups are, again, they're probably the easiest possible way to get a conceptual handle on what's important in a system. So the example that I have, one that we haven't seen before, it's called the Froude number. So the Froude number, it's a dimensionless, it's a ratio of inertia to gravity, inertial forces to gravity. So inertial forces, that's rho v squared, gravity, rho gh. So you're looking at the ratio of these two forces. Okay, really, that's the Froude number squared, but that's just kind of a weird definition thing. But the Froude number is this ratio of forces. So you can tell without doing any fancy calculations, if you look at this ratio of parameters, you look at the dimensionless group, you can tell without doing anything fancy what is kind of governing the system. Is inertia and velocity governing the system, or are gravity and pressure or gravity governing the system or governing the flow? So if you think of an example where the Froude number is really big, that means inertia is winning, and inertia is really the thing that matters. That would be like drag force on a rocket. So what matters in drag force on a rocket? Well, gravity doesn't really play a role. It's just like the fluid flowing against the rocket. The effects of gravity are basically non-existent. Different example, if you have a really big boat moving through water, if a boat's moving through water, the Froude number is like ballpark 1. Maybe not exactly 1, maybe it's like 5 or 0.2 or something like that, but it's close-ish to 1. It's not 1,000. So what that means is the drag on a boat depends both on how fast you're going. It depends on inertia and like how fast the fluid is moving, but it also has something to do with gravity. And like the waves of the boat actually contribute to the waves of the water contribute to drag forces on a boat. So you can't neglect gravity and drag on a boat, but you can neglect gravity when you're thinking about drag on a rocket or on an airplane or something like that, or even on a car. Another example, Froude number way less than 1. That would be a flow that really gravity is winning and inertial effects aren't really doing much. So a slow moving river is pretty much, you can just look at gravity and you don't really have to consider velocity, right? The limit where velocity is 0 is just hydrostatics, where you're completely just governed by gravity. And gravity is the only thing that's giving you like pressure differences and the only thing that's influencing your fluid. So that's one example. We've dealt a little bit with Reynolds number. One example from one we haven't dealt with called the Froude number. There are a whole bunch of other dimensionless groups. This is a couple from a list of a whole bunch. I think a large reason why there are so many is because if you're, say, Reynolds, then you get your own number, and that's kind of fancy. So there are some that are a little bit half-hearted attempts at like getting your own number, where it's like I took two other people's numbers and multiplied them together, and I'm going to call that mine. There are a lot like that. They're actually useful in certain situations, but I took fluids from a professor who had his own dimensionless group, which was kind of exciting. So it's like super specialized, but then that was his dimensionless group. Most of these you probably haven't heard of. Some you have, right? I'm sure all of you have heard of the Mach number. It's a dimensionless ratio of velocity to the speed of sound in a material. But it's a ratio of, we know it as that. We know it like Mach 1 is the speed of sound. But it's a ratio of velocities in a system to the compressibility of the fluid. And the speed that sound travels through a fluid is related to compressibility and density changes. How fast do density variations move in a fluid? So inertial to compressibility. So if you want to know, are compressibility effects going to be important? You can look at the Mach number. And if you're above like Mach 0.3, compressibility starts to matter. And density changes because of the velocity are going to start to matter. The Weber number. If you're looking at, say, a pumped hydro system, surface tension of water has nothing to do with what's happening. It doesn't matter at all. You can totally forget it. None of you have started to try to incorporate surface tension into the models of what's happening, and that's good because it doesn't matter. If instead of a really big pumped hydro system, you were trying to look at, say, a really thin film of liquid, then surface tension actually probably is important. How do you know when it is and when it isn't? Well, you can just calculate the Weber number. And if it's about 1, then surface tension is important and velocity are important. If it's really big, velocity wins, inertia wins. If it's really, really small, like say a drop sitting on the windshield on your car, that's like just sliding slowly up the windshield. Well, the fluid behavior is almost totally governed by surface tension. That's why it stays a drop as it slowly moves up your windshield. Because surface tension is winning. So that would be a system that has right, the bottom, that would be a really small Weber number. So you can get a sense of like what forces are important, what factors are important, what ones can I cross out. I think we always have a tough time in engineering, like figuring out if you're given a new problem that you've never thought about before, what forces, what assumptions can I make? Like, is gravity important or not? I don't know. Sometimes I don't know. If you can go to the dimensionless groups, you can do without a whole lot of work, right? This is plug in a couple things in your calculator. Is gravity important? You can figure it out in 30 seconds. Surface tension, I don't know if that's important. I've never really looked at this fluid or this size system. We'll spend 30 seconds, calculate the Weber number. Is surface tension going to be important? So that's with the power of some of these groups, where you can look at, without really any advanced calculation, you can get intuition as to what factors are going to matter and what factors aren't. Okay, just one more that I'll talk about, the cavitation number. So we talked, I don't know, we spent like a day talking kind of in different ways about cavitation in fluids, where what can happen is you go from the liquid state to the gas state, like say at a valve or something like that because of pressure changes in the fluid. Is that going to happen or not in your system? How are you supposed to know? Well, you can really easily calculate the cavitation number, which is the ratio of the pressure to the vapor pressure, or pressure minus vapor pressure over inertia. Is cavitation going to be something that you should worry about in this system? And you don't have to do anything super fancy. You just spend like 2 minutes and you can get a sense of whether that's going to be something to worry about or not. So dimensionless groups can be a really like low effort way to get intuition on what factors are going to matter in a system that maybe you haven't thought about. So there's kind of a low effort, high value way to develop intuition about problems. We're also going to see a little bit in a second, well, probably on Monday, when we can actually, or another way that we can use some of these dimensionless groups. But right now, we're going to look like all of these, like that grouping of variables, even this grouping of variables, it's the Reynolds number, so maybe you're used to it, but it's kind of weird. Like mu, rho, v, L, GL over V squared, like how do you figure those out? So we're going to look briefly kind of at where those come from. And we'll look at, it's called the Buckingham, not Buckingham, it's not going to let me erase it. That's bunk. Erase it. Stop it. Okay. Called the Buckingham Pi Theorem. So this is a formalized look at dimensionless groups, trying to get a formalized picture of where we come up with these and how they fit together. So we'll do this by looking at an example where we have drag force on a sphere. So drag force on a sphere. We have a sphere and some fluid flowing against the sphere. We are interested in drag force, and we're trying to see what does it depend on. So F drag what variables or factors in our flow is drag force, or in our system, is drag force going to depend on? Any ideas? Like if we change it, we would get a change in drag force. Velocity. Anything else?
The shape, so whether it's flat or
okay, so it's always gonna be a sphere. We're gonna look just at a sphere. So I agree with what slight variation on shape. If you have a small sphere or a big sphere, are those gonna be the same or different? Different, so diameter. I saw, was somebody else going to say diameter? Diameter. So pressure is going to change it, but it's going to change it because of density. So the density of the fluid matters. What else? Yes, we're going to be looking at geometrically exactly the same. So let's say, look just at, so yes, that would change it, but that's changing the shape. So we're still keeping shape the same. What if we did this with air flowing at 10 meters per second, or water flowing at 10 meters per second, or syrup flowing at 10 meters per second? Would those be different? Because of changes in what? Density, but also viscosity. Okay, so those are going to be the four main things, where if we change any of those, we change the drag force. So drag force is a function of those four things. And like we kind of touched on last time, if we wanted to get an idea of how it depends on all of these, we could do experiments where we're changing all of them, but that gets quite cumbersome. So what we want to do is boil it down as much as we can and not look at how drag force depends on all of these, but how they kind of all work together, because they're not totally independent. So we want to so F drag, which is some function of V d rho mu to a dimensionless a dimensionless equation where pi 1 is some function g of pi 2 pi, we'll do little dot, 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 pi n. Right, so this would be like a dimensionless drag, and these would be dimensionless variables. And this only is helpful if if we kind of boil it down so there are less variables in the system after we do this than there were before. So before there are 5 variables, we have drag force depending on 4 other things. So hopefully after we go through this, there are less than 5 things. Like maybe we get 1 thing depending on 2 other things instead of depending on 4, for example. So we're trying to kind of boil it down so that there are less moving pieces, there are less variables in the system. Okay, so it will look easier to understand as we actually go through it. So let's go through, it's kind of a formalized procedure, so we're going to go through all the steps of this procedure. So step 1. Step 1 is list all important parameters. Okay, so we already did that. We have F drag, which is a function of d v rho mu. So how many parameters we have? These are all our parameters. N equals the number of parameters. So N equals 5. 5 total parameters. Step 2. Step 2, we're going to list in terms of the primary dimensions. Okay, so what do I mean by primary dimensions? What's a primary dimension? Something like length. Length is a primary dimension. I saw one back in the back. Time. Any other primary dimensions? Think of like a unit that you can't break up into other units. Like a Newton, you can break up into kilograms and meters and seconds. Mass. We'll call that capital M. Any other ones? Yep. Temperature.
Brightness.
Often run into that in fluids, but you would in heat transfer. Any other ones? Charges, yeah. You can't break up a charge into like mass or temperature or something. So charges. Okay, those are the most common ones. Those are primary dimensions. You can't split them up. We're going to break our variables or our parameters up into their primary dimensions. So let's make a table. So we have a param, we have the units, and its dimension. So we'll start with drag force. What are units on drag force? It's a force. What are the units? Like a Newton. Appreciate you staying in metric. What are the dimensions of newtons? If you break it up, it's what? Like break it up into mass, length, and time, temperature and charge, but there's no temperature or charge in a Newton. So it's a mass times a length divided by a time squared, like a kilogram meter per second per second. So mass length over time squared. What about diameter? What are the units on diameter? Like a meter, which is a length. Density. Units on density. Kilogram per meter cubed. So our dimensions are mass per length cubed. Velocity, we'll save the best for last. So velocity, something like a meter per second. So that is a length per time. What about, is the surprise bonus round. What are the units on viscosity? Does anybody know? I would have to look it up. So a Newton second per meter squared. Okay, viscosity, so we have to break that up into its dimensions. So we have newtons, which are made up of meters length or mass length per time squared, times time divided by meters squared. So this is mass per length time. Okay, so we break them up break all of our terms up into their dimensions. And then we let a variable r equal the number of primary dimensions. So, for this case, r equals 3. We have 3 different dimensions. We only have mass, length, and time. All right, step 3. Step 3, I'll write this and then we'll do it and hopefully it will become more clear. We're going to select R repeating parameters that include all primary dimensions. Okay, and this has 2 caveats. So this has to be, they can't just differ by an exponent. So like a diameter and an area have, so we said so the diameter of the sphere is what matters. You could have said, well, what about the area of this, like the surface area of the sphere? And I would have said, yes, the surface area matters, but it's not independent of diameter because they differ by just an exponent. There are some situations where that's not super clear that those are like different, that those are not different things, like it is maybe with a diameter and area. But they can't just differ by an exponent. And we can't choose our dependent parameter. So we can't choose f drag. Okay, so basically what we're trying to do, we're going to go up to this list. So this table up here, we want to choose 3 things between the list of diameter, density, velocity, viscosity. We have to choose 3 of those, and we have to choose them so that all 3 of our primary dimensions are represented. So we have to make sure that we like choose ones that have length, mass, and time. There's not a way in this case to choose 3 and not have them satisfy this, but in some cases there might be. So we're going to choose, we'll choose diameter, density, and velocity, right? So diameter has dimensions of length, density has dimensions of mass per length cubed, velocity has dimensions of length per time. So we have all 3 of those represented, mass, length, and time. Okay, between the 3 of them. There's no like added bonus points for choosing one that one by itself has all 3, like viscosity. You just have to get all 3 covered with the 3 that you have to get all of them covered with the ones that you choose. Okay, so the last step that we'll talk about today, which is not quite the last step, but the second to last step, is then step 4, we're going to determine the number of dimensionless groups. Okay, so we will have m minus n groups, m minus n dimensionless groups, where n is the number of parameters, right? So for our example, n is 5. We had 5 different parameters: drag force, diameter, velocity, density, viscosity. And m is equal to r, typically, usually, not always, sometimes there are exceptions, but usually it's equal to r. So in this case, r is 3. So we have 5 minus 3 equals 2. Two-dimensionless groups. So that's the power of kind of this method and this way of thinking, is we can take a problem that originally has 5 different variables that we're trying to juggle. We can do this and boil it down to just 2 things. Thing A depends on thing B. Or you can boil it down maybe from 6 or 7 variables down to 3. So thing A depends on only B and C, or only 2 and 3. So that's what we're trying to do. We'll pick up and finish that on Monday with step 5, where we actually kind of combine this and get our dimensionless groups. Hope you guys have a good weekend. Yeah, feel free to email me if you have questions as you're working through this, as you're working through your project.